Okay, so today we're going to be introducing how to use trigonometric identities for one of the first times. Now, these are basically a way of reorganizing equations and expressions to something that may be difficult to understand into something that is more easily understood. Most of the time when we rewrite them, we're rewriting them to some version of a special right triangle, a 30-60-90 or a 45-45-90. And there's going to be a lot of flipping around and changing things about. So to begin, the first few things that we're going to fill out is we're going to fill out our following reciprocal, quotient, Pythagorean, cofunction, and even odd identities. So I'm going to go ahead and I'm going to pop these on the screen. If you want to go ahead and pause it, you may. Unpause it when you're done so that you've got all these copied down. Now, realize with these, most of these we're going to have to use, and these should feel relatively familiar. We're going to stick with mostly things that deal with sines and cosines. So albeit this looks like a lot, we're really only dealing with a handful of these things. These in and of themselves we're going to have to use to eventually relate back to the sines and cosines, but everything else after this point, there's a couple ways to work most of these problems. The basic is going to be working them with sines and cosines predominantly, and that's what we're gonna stick with. So now that you've copied those down, let's take a look at the first one. Now, this front page really doesn't involve too many of those identities up front, but it will get us used to how do we set up expressions and how do we get used to flipping around things like sines, cosines, secants, and things like that. So when I look at this, I'm going to say I need to evaluate all 6 trigonometric functions. So for number 1, I'm going to say the secant is equal to -5/2. And also I know that the secant is equal to 1 over the cosine. And if I know that the cosine is equal to the adjacent over the hypotenuse, or the adjacent in this case being the x over the r, the secant, what it gave me was the radius over the x value. And so I'm going to say, okay, that's going to be the radius over the x value. Why didn't I put the negative with the radius? Well, because the radius can't be negative. And so I'm going to look at the unit circle, and I'm going to say, okay, I have 2 choices. I have an x value of -2. Let's just go ahead and put that in there, and let's do it in black. So -2. And I have a radius that can either go up here or it can go down here. Don't know which one just yet, but I know one of those is going to be my radius. Well, this information is going to tell me which one, top or bottom. So let's take a look at this. So the tangent of x, so the tangent is going to be equal to the y, not over the r, y over the x. And if it's less than 0, that means that this is going to be a negative number. Well, I know that my x is negative, so the only way that this will work is if I take a -2. The only way that I'll get a negative number is not by putting another negative on top, is by putting a positive on top, which means that my y value must be positive. So I'm dealing with this triangle right here. So let's go ahead and fill out this triangle. Well, if that was -2, that must mean that this is 5. I need to figure out what my y value is. So for my y value, let's go ahead and, why not, let's do this in red. I'm going to set up the Pythagorean theorem. A squared plus b squared equals c squared, which means that my a squared is going to be -2 squared, plus my b squared, which is y, my c squared, which is 5 squared, which is 25. Subtract the 4. Y is equal to the square root of 21. Now I know it could be either the positive or the negative square root of 21, but I'm not concerning myself with the negative, only with the positive. Boom, there we go. And so with this information, we can set up all 6 trig functions. So if I set up sine, cosine, or tangent, sine is just opposite over hypotenuse, which is going to be the square root of 21 over 5. Cosine is adjacent over the hypotenuse, so -2 over 5. Notice how it's just flipped. And then tangent is going to be the opposite over the adjacent, square root of 21 over -2. And for the other we have cosecant, secant, and cotangent. Secant we already know. We get -5/2. We're just flipping this version. But for cosecant and cotangent, when we flip them, we're going to have a radical on the bottom, which we can't have. So I'm going to say 5, and I would have the square root of 21. So I'm going to multiply that by another square root of 21, which is going to put that up top. Same thing with cotangent. It would be a -2 over the square root of 21, but I can't have a square root in the bottom, so I multiply top and bottom by another square root of 21, which gets that out of there. And we've got those 6 trig functions. So that's that. Let's try another one of those. So with this one, we have the sine of theta is equal to -3/4. So let's take a look. Let's see. Sine is going to be equal to the y over the radius, which means that my radius has to be positive. So that must mean my y value is negative. So if I'm setting up a unit circle, that means I'm dealing with one of 2 different shapes. If my y value is -3 and my radius is 4, I'm dealing with one of those two triangles, which means that, quite honestly, this cosine is going to tell us which one am I actually dealing with. Well, the cosine, it tells us, is going to be greater than 0. And we know that the cosine is going to be equal to the x over the radius. Well, my radius must be positive, which means my x must be positive. Okay. So if my x is positive, I'm dealing with this triangle. Awesome. And so again, I'll set up the Pythagorean theorem to figure out what this x value is. So what I get is I'm going to end up getting, let's do this in red just to keep it consistent. A squared, which is going to be my x squared, plus b squared, which is a -3 squared, which is 9, is equal to my c squared, which is going to be 16. If I take 9 from 16, let's see, that's going to give me 7. Arithmetic is a little hard right now. So that's going to be x equals the square root of 7. Okay. So if I have the square root of 7 right here, that's going to tell us everything we need to know about all 3 of these trig functions. So I'll have sine, actually it's of theta, cosine of theta, and the tangent of theta. And then I'll have the flipped versions as well of the cosecant, the secant, and the cotangent. So what I know is that the sine, dealing with only this triangle right here, is going to be the opposite over the hypotenuse, so -3/4, which is what we had right here. Cosine is the adjacent, so we get the square root of 7 over 4, and the tangent is opposite over this. So it would be -3 over the square root of 7, which we know we can't have, so I rationalize it by bringing it to the top. Cosecant, we flip it, so -4/3. Secant, we flip this, so it's going to be 4 again over the square root of 7, which I know I can't have, so I'm going to bring it to the top by multiplying top and bottom. Cotangent, if that was going to be -3 over the square root of 7, we can just go ahead and flip that as square root of 7 over -3. Boom. And there we go. So now that you've seen 2 questions in action, why don't you go ahead and try out number 5, pause the video, unpause it when you're done, and see how well you did. Okay. So we've got the tangent of phi is equal to 2/3, and the cosine of phi is going to be greater than 0. So let's see. Tangent is going to be equal to y over x, which means that this could either be a +2 over a +3 or a -2 over -3, because they're both going to reduce down to being the same thing. So a tangent's a little trickier. This is going to give us, okay, if I have a +2, +3, dealing with that triangle, or a -2, -3, I'm going to be dealing with that triangle. So which one is it going to be? cosine is going to tell us which. The cosine is going to tell us what the x over the radius is. And if the x over the radius is greater than 0, that means the x is going to be greater than 0, which means it's got to be this one on the right. So it's got to be this one right here. And so if my y value is 2, my x value is 3, Pythagorean theorem, so that's 2 squared, which is 4, plus 9 is equal to the radius squared. The radius is the square root of 13. So for the sine of phi, the cosine of phi, and the tangent of phi, sine is opposite over hypotenuse, which is going to be 2 over the square root of 13. Can't have that. Cosine is adjacent over hypotenuse, which is going to be 3 over the square root of 13. Can't have that. The tangent is opposite over adjacent. If I have the cosecant, the secant, and the cotangent. So cosecant is that flipped, which I knew was originally square root of 13 over 2. Secant is that flipped, which I know was originally square root of 13 over 3. And the cotangent is that flipped, which is 3/2. So for those questions, they dealt mostly with reciprocal functions. But for the next set of questions, we're going to kind of flex our mental muscles a little bit more. And we're going to reorganize the expressions on the left and match them with the expressions on the right. So we're going to have to rewrite these, and we're going to use most of these other functions so that we can match them up with something over there on the left-hand side. So there's a couple ways to work these, and I'm going to work one way consistently. And we're not really going to see it number 1, we're going to see it number 3, but I'll explain it when we get there. So how do I rewrite this into a different expression? So our first thought is whenever I see anything that is either a tangent, a cotangent, a secant, or a cosecant, I am going to rewrite them into terms of sine and cosine. That's going to be our number 1 rule, is anytime I see anything like that, rewrite them in sine and cosine and try and condense the expression as much as possible. Which means the secant, I'm going to rewrite the secant as 1 over the cosine of x, which immediately shows you what's going on here. Cosine of x divided by the cosine of x is going to be equal to 1. And if we come over here and scan our available options, we see that we have option C is going to be our value of 1. Boom. So we get option C. For number 3, we're going to do the same thing. Anytime I see a tangent, a cotangent, a secant or cosecant, I'm going to rewrite them as sine or cosine. Now, that being said, we notice that this is one of the Pythagorean identities. We can solve this very quickly by using that tangent aspect of the Pythagorean identity. The way that we're going to do takes a little bit longer, but it's going to be much more clearly understood, and it's going to be easier to work if we follow this approach. Albeit I see a faster approach, that just necessarily means that we need to remember a lot more formulas, which is going to be a little difficult over time. You're going to end up using a handful of them most often. So why not get practice with those handful that you're going to end up using the most? So let's get started with this one. I'm going to rewrite this tangent function as a sine over cosine. So cosine of x, 1 plus sine squared x over cosine squared x. I have to keep it as a squared because it was a tangent squared. And then now what I'm going to do is I'm going to try and combine these as best I can. I have 1 plus this, which means I need to take this 1 and combine it with this fraction over here. So I'm going to multiply the top and the bottom of 1 by the cosine of square root of x in order to add the two tops. So cosine squared of x times the top and times the bottom so that I can add these two fractions. Now what we see is that original identity that we were going to use here pops up again with the sines and the cosines. And again, it's just a little less to remember. But I notice that the cosine squared of x plus sine squared of x, if I rewrite that, is going to be equal to 1. So I have the cosine of x times 1 over cosine squared of x. I notice this can partially reduce, not the whole thing, but I notice that can go away. And one of those cosine of x goes away. So I'm left with 1 over cosine of x, which is equal to, if I need to fully reduce it, the secant of x. I rewrote that as a single trigonometric function. Which if I go down my list and say, where does my secant of x exist? Yes, I have one of my options, which is a secant of x. So option F. Perfect. So now that you've kind of seen how that's done, why don't you go ahead and take a shot at one of your own. Pause the video on number 5, unpause what you're doing, and see how you did. Okay, so on number 5, again, the first thing I'm always going to do is I'm going to rewrite anything that is not a sine or a cosine as a sine or cosine. So I'm going to write the secant squared of x as 1 over the cosine squared of x, all over sine squared of x. And again, it looks like I made it more complicated, but it's going to end up working itself out a lot more nicely. So I need to go ahead and combine this minus 1 with this fraction over here so that I can eventually keep, change, flip, and combine top and bottom. So if I'm subtracting a 1, I'm going to multiply top and bottom times cosine squared of x over cosine squared of x. So that's going to leave me with 1 over cosine squared of x, and I multiply top and bottom over here, cosine squared of x. And remember, this is all over sine squared of x. And so what we notice right here is that I have 1 minus the cosine squared of x. And now this doesn't look exactly like a Pythagorean theorem or a Pythagorean identity. It is, because let's take a look. So sine squared of x plus cosine squared of x is equal to 1, which means that if I take this cosine and move it over there, sine squared of x equals 1 minus the cosine squared of x. Again, this is one of the ways that we need to rewrite it, which is why I strongly recommend that we write these as sines and cosines. Because if I'm going to have to recognize every variation of one of these, it's a lot easier to do than memorizing every variation of 3 of these. So I'm going to rewrite this 1 minus cosine squared of x as a sine squared of x. Boom. So I get that. Which then this leads us to, I can now keep, change, flip, which is going to take my sine squared of x over cosine squared of x, and I'm going to flip this, which was over 1, multiply it times 1 over sine squared of x, which we notice in that case, they cancel out. I have 1 over cosine squared of x, and if I want to rewrite that as a single trig function, that's going to be rewritten as the secant squared of x. And so let's see, where do I have a secant squared of x in my list? Oh, secant squared of x is g. Perfect. So I think we've got the hang of it. We rewrite them as sine and cosine and then renegotiate it until I can get down to something as simple as possible. So again, why don't you pause the video on number 7, unpause it when you're done and see how you did. Okay. So now that you have a chance to work it out, I notice these are already in sines and cosines, so I don't really have a whole lot to do, but I can go ahead and factor out a sine, which leaves me with the cosine squared of x minus 1. And again, we spoke about recognizing variations of the same theme. Well, if the sine squared of x plus the cosine squared of x is equal to 1, I bet you if I subtracted that 1 and subtracted that sine squared of x, I'd get something that looks like this. So really all I want is I want to get one of these sides of the equation, minus 1, I move that over here, to look similar. And then whatever else I need to do with the rest of it, do with the rest of it. So that means I subtracted the sine squared of x. I have that, I can replace it with the sine squared of x, or negative sine squared of x, I should say. So I get sine of x times negative sine squared of x, which leads me to the negative sine cubed of x. So negative sine cubed of x, let's take a look. Boom, option D. Boom, and there we go.